Hello everyone. Let's embark on a journey into the intricate world of 3D graphics, where what you see isn't always what you get. Hidden surface removal is the behind the scenes magic that transforms flat images into immersive 3 dimensional experiences. In this presentation, we will uncover the secrets behind this essential process and discover how it enhances realism in computer generated world. Let's start, or as we dive in, let's first grasp the challenge posed by hidden surface and why addressing them is fundamental to creating immersive 3D environments. Now, start with the introduction to the hidden surface removal. Now, as the hidden surface removal is a fundamental technique and in a computer graphics that determines which surfaces are visible and which are hidden from viewers' perspective. This is crucial for creating realistic and accurate 3D scenes. And hidden surface removal is also known as hidden surface elimination or occlusion cooling. In the process of determining which surfaces or a part of the surfaces in a 3 dimensional scenes are visible to an observer and which one are obscured by the other surfaces. Now, let's talk about the importance. Now, the importance of the hidden surface removal. Realism, efficiency, depth perceptions are we know. In computer graphics, the goal is to create images that accurately represent a 3 dimensional scene. If you don't remove the hidden surface, you will end up with the images where the objects appear to intersect or penetrate each other incorrectly, resulting in visual artifacts and inaccuracies. So, the importance with the realism means the proper handling hidden surfaces is essential for generating a 3D environments. Now, the efficiency, removing the hidden surface reduces the amount of rendering works required or improving the performance and efficiency and depth perceptions. Now, next with principles. As a principles of Z buffer. As the basic techniques for the hidden surface removals are we seen with the Painter's algorithms or Z buffer algorithm or binary space partitions in computer graphics with the hidden surface removal. Now, let's talk about the principle of Z buffer algorithm. There is having of a depth comparison, depth storage and occlusion testing. The Z buffer algorithm involves the depth of each pixel in a separate buffer. During the rendering, for each pixel, the algorithm checks if the new object behind the rendered is closer to the viewer than the previous rendered object at that pixel. If it is the new object is drawn and its depth value is updated in the buffer, this technique is widely used due to its simplicity and effectiveness. Now, the algorithm or how the Z buffer algorithm works. Initialize a Z buffer means the Z buffer is initialized to the maximum possible depth value and representing an empty scenes. Next one, rendered polygon means the polygon are rendered in any order with their depth value and compared to the Z buffer. And next step is update the Z buffer. If the polygon depth is closer than the current Z buffer value, the Z buffer is updated with the new depth. This is nothing but the Z buffer with its calculations and algorithm, how it works and how the X and Y are defining with the Z buffer and how the pixels or working of pixels are we needed for the Z buffer. Now, the next slide with the advantages. First of all, the Z buffer algorithms are widely used due to its simplicity and effectiveness, also having of flexibility, efficiency, and robustness. In a simplicity, the Z buffer algorithm are relatively straightforward to implement, making it widely adopted in a computer graphics. And flexibility, with it can handle arbitrary polygon order and supports a complex 3D scenes with minimal processing effectiveness or the efficiency. The Z buffer algorithm can be a highly optimized for real time rendering, such as in video games and simulations. Robustness, it can handle a wide range of geometries, including the intersections and overlapping polygons without special cases. So those are going with the Z buffer algorithms, which are being used widely with those of applications or advantages. Now next with limitations. Everything which comes out with its limitations. Now the limitation of Z buffer. Now the memory intensive. Z buffer requires storing a depth value for every pixel which are consume a significant memory for the high resolution. Z buffer consumes a memory intensive. Next, the precision issue. So the floating point precision errors can cause artifacts, and those are comes with the Z buffer algorithms or the Z buffer. Then transparency challenges. The Z buffer algorithm struggles with the transparencies or semi-transparent surfaces which require a special handling for that. So these are with the Z buffer algorithm. Next one is sorting limitation. The algorithm cannot correctly handle scenes with a complex order, dependent visual effects such as refractions, etc. So those are all limitations of Z buffer algorithm. So now talk about the applications. So everything comes out with its special applications where we are studying that. So the basically Z buffer algorithms are having various applications or very important applications in computer graphics, medical imaging, and scientific visualizations. As the hidden surface removal is a fundamental in a various application including the video games, computer aided design as CAD, virtual reality, and simulations where the rendering realistic scenes in a real time is crucial for user experience and interaction. In the computer graphics, Z buffer algorithm is a de facto standard for hidden surface removal in real time 3D rendering used in video games, simulation, and computer aided design software, etc. Medical imaging. It is employed in 3D medical imaging technologies such as CT scans and MRIs to visualize the internal structure of the human bodies. Now, in a scientific visualization, the Z buffer algorithm is crucial for accurately depicting a complex 3D data such as molecular structures, weather patterns, and scientific simulation. So, those are all points are go with Z buffer algorithms. Now, next with a conclusion. So, the Z buffer algorithm is a fundamental technique in a computer graphics that enables the accurate rendering of 3D scenes by determining visible surfaces, and its simplicity, flexibility, and efficiency have made it a widely adopted and essential tool in a field. So, the hidden surface removal is a crucial aspect of computer graphics that ensure that the rendering image accurately represent the geometry of 3D dimensional scenes from the viewer's perspective. As the future development ongoing with the research aims to address the limitations of the Z buffer algorithm, such as improving the precision, handling the transparency, and expanding support for complex visual effects, emerging techniques like deferred rendering and GPU accelerated algorithms continue to advance the state of the art in hidden surface removals. So basically, those all are the future developments that all comes with the Z buffer algorithm. So all of this works with the hidden surface removal for us to view, to create, or to enhance with that technology and to understand how it works, or how the behind scene it will gives us the output with such beautiful things and such 3D images